For this SATSOFT Under the Hood tutorial, I'd like to discuss some of the inner workings of SATSOFT. I'll start with a discussion of the coordinate system that relates the spacecraft antenna to the Earth. Then I'll talk about the antenna models used in SATSOFT and present some of the equations used. I'll define component beams and composite patterns. I'll talk a bit about the optimizer and then present a flowchart on the shape beam antenna synthesis as performed by SATSOFT. This is the coordinate system that is used to relate the spacecraft antenna to the Earth. The antenna is located at the origin, which is directly above nadir. The x-axis points in the velocity vector, at least for a geospacecraft. Azimuth is defined positive to the east. Elevation is positive to the north. The z-axis points away from the Earth, and so a rotation of 180 degrees about the y-axis is necessary for the antenna. The Gaussian beam model is included with SATSOFT. All of the rest of the models are optional. There's two reflector models, a simplified analytic model and a high-fidelity physical optics reflector model. There's an analytic phased array model, and there's also a more fully featured phased array program, which is still in development. The Gaussian beam model gets its name from the Gaussian probability density function, where beam center is at the mean and the standard deviation is the 3 dB beam width in the x and y directions. This does not model any particular physical type of antenna, so the directivity is not accurate. Even in a gain area product sense, the gain is not accurate. In fact, you can set the efficiency to anything you want, and so set the directivity to whatever you want. 10 log f is the directivity in dB. Note that beam shape is parabolic in terms of dB. The model is good for drawing pretty pictures like this. It's very easy to use. You enter the major and minor beam widths, and the rotation of the beam can be achieved using the boresight rotation in SATSOFT. SATSOFT AR is a simple analytic model of an offset paraboloid fed by an array of single or dual mode circular feed horns. Illumination taper and spillover loss are accounted for, but scan aberration and cross pole are not. It's a simple scalar model describing the amplitude of the pattern. The phase is set to 0. You cannot accurately determine the weights of a beamforming network using this model, but it is useful for preliminary work in shaping patterns, determining reflector size, minimum coverage area gain, and average side lobe level. It most closely approximates reflectors with large f over d ratios, where f is the focal length and d is the diameter of the aperture. This shows the elimination function of the analytic reflector model. It's limited to a circular aperture of radius a. P is the excitation at the edge of the aperture, and f is the far-field pattern, which is given by a linear combination of Bessel functions. Note that if n is 0, the elimination function reduces to a uniformly illuminated circular aperture, of which the far-field pattern is then given by j1x over x. Alpha and beta depend on the edge taper p and are normalized so that the square of f gives the directivity of the pattern in dB. The actual directivity is determined by a physical optics integration of the aperture using an on-focus feed. This is a grid of beamlets computed using the analytic reflector model. Each beamlet corresponds to a feed horn in the focal plane of the reflector antenna. All of the beamlets are identical since they're computed from the analytic function that I just showed. The inset shows the side lobe structure, and note that the pattern is circularly symmetric. This is a pattern computed with the analytic reflector model overlaid with that computed from the physical optics model for an on-focus feed. Notice that the patterns overlay very well. But as the feed is scanned away from boresight, the two patterns will start to diverge.